There is a place in our solar system where rain falls from orange skies, where rivers carve their way across frozen ground, winding through valleys and emptying into dark, still seas that have never reflected sunlight directly. A place where the air is thicker than the air you breathe right now, where clouds gather and storms roll across landscapes shaped by forces that feel strangely, hauntingly familiar. This place is not a planet, it is a moon, and it orbits Saturn at a distance so great that sunlight arrives as little more than a cold whisper, roughly 100 times fainter than what reaches Earth. Its name is Titan. Among the hundreds of moons scattered across our solar system, Titan holds a position unlike any other. It is the second largest moon of all, surpassed only by Jupiter's Ganymede, and it is larger in diameter than the planet Mercury. But size alone is not what makes Titan extraordinary. What sets it apart, what has captivated planetary scientists for generations, is something far more unusual. Titan possesses a thick, dense atmosphere, a real atmosphere, one composed primarily of nitrogen, just as Earth's is, but enriched with methane and laced with complex organic molecules that paint the sky in shades of deep orange and hazy gold. No other moon in the solar system has anything like it. The atmospheres of other large moons, where they exist at all, are thin traces of gas barely clinging to their surfaces. Titan's atmosphere, by contrast, extends hundreds of kilometers above its surface and exerts a pressure at ground level roughly 50% greater than sea level pressure on Earth. If you stood on Titan's surface, you would feel that atmosphere pressing gently against you, heavier than the air of your own world. For centuries, this atmosphere kept Titan's surface completely hidden. When astronomers pointed their telescopes towards Saturn's largest moon, they saw only a featureless orb wrapped in unbroken haze. No craters, no mountains, no plains, just a smooth, impenetrable veil that offered no hint of what lay beneath. Titan became one of the great unsolved puzzles of the solar system, a world whose surface remained more mysterious than the surfaces of planets billions of kilometers farther away. And then, at the beginning of the 21st century, humanity sent a spacecraft to find out what Titan was hiding. What it discovered was a world that no one had fully anticipated. A world with methane seas stretching across its polar regions, with shorelines and islands and submerged channels. A world with vast equatorial dune fields sculpted by winds into long parallel ridges running for hundreds of kilometers. A world with river networks that resembled drainage systems on Earth so closely that the comparison was not poetic but geological. A world with seasons, weather patterns, and a methane cycle that mirrors, in broad and beautiful strokes, the water cycle that sustains life on our own planet. Titan is not Earth. Its rivers do not carry water. Its rain is not something you could stand beneath and feel refreshed by. Its seas would not sustain a single organism from our world. The temperatures at its surface hover around minus 179 degrees Celsius, cold enough that water ice behaves like rock, and methane flows as freely as water does here. It is an alien world in the deepest sense. And yet, Titan feels familiar. It feels like a place, not a barren rock drifting in silence, not a cratered relic frozen in time, but a living, active, evolving world where things happen, where weather moves, where landscapes change, where the surface tells a story that is still being written. Tonight we travel there, not quickly, not in summary, but slowly, carefully, the way a world this rich deserves to be explored. We will begin with the moment Titan was first noticed by human eyes, a small point of light beside Saturn that a Dutch astronomer recorded in 1655. We will follow the centuries of wondering, the decades of planning, and the long journey of a spacecraft named Cassini and its small passenger, a probe named Huygens, which would eventually descend through Titan's atmosphere and touch its surface for the first and only time. We will walk through that atmosphere layer by layer, understanding how sunlight interacts with methane and nitrogen to create the complex orange haze that blankets the moon. We will map the surface as Cassini's radar revealed it, pass by pass, strip by strip, slowly pulling back the curtain on a world that had remained hidden for as long as humans had looked at it. We will stand at the shores of methane seas, trace the paths of hydrocarbon rivers, cross dune fields shaped by winds that blow at the edge of perception, and consider the extraordinary possibility that beneath Titan's frozen crust, a vast ocean of liquid water may quietly exist, waiting. This is the story of a world that is simultaneously ancient and active, frozen and flowing, alien and yet strangely recognizable. A moon that challenges our assumptions about where familiar processes can occur and what the word habitable might truly mean when freed from the narrow conditions of Earth. This is Titan. The story of Titan begins not with a spacecraft, but with a telescope, a modest instrument by modern standards, assembled from hand-ground lenses in the workshop of a Dutch mathematician and astronomer named Christian Huygens. It was the year 1655, and Huygens had been refining his lens grinding techniques with considerable patience, producing optics that were, for their time, remarkably sharp. His telescope was not the largest in Europe, but its clarity surpassed many of its contemporaries, and Huygens had turned it toward a target that had fascinated astronomers since Galileo first observed it decades earlier. Saturn. Galileo himself had noticed something strange about Saturn as early as 1610. Through his own small telescope, the planet appeared to have odd protrusions on either side, almost as though it had ears or was accompanied by two smaller bodies pressed against it. He could not resolve what he was seeing. The rings of Saturn, so familiar to us now, were beyond the resolving power of his instrument, and Galileo never fully understood what he had observed. He died without knowing that Saturn was encircled by one of the most beautiful structures in the solar system. It was Huygens who, decades later, proposed that what others had seen as lumps, handles, and companion stars was in fact a flat ring surrounding the planet, inclined at an angle to our line of sight. And it was during these careful observations of Saturn and its ring that Huygens noticed something else. A small point of light, faint but unmistakable, appearing near the planet and moving with it across the sky over the course of several nights. He tracked it carefully. The object was not a background star. It moved in step with Saturn, circling the planet, with a period he estimated at roughly 16 days. Huygens had discovered a moon. He named it simply Saturni Luna, the moon of Saturn. It would later be given the name Titan. At the time, this was an extraordinary discovery. Only 4 moons were known in the entire solar system beyond our own, the 4 Galilean moons of Jupiter, discovered by Galileo in 1610. Titan became the 5th known moon of any planet and the first moon discovered orbiting Saturn. Huygens published his finding in a short work and continued his observations, but the tools of his era could reveal nothing more. Titan remained a point of light, its nature entirely unknown. In the centuries that followed, other astronomers discovered additional moons around Saturn. Giovanni Cassini, the Italian-French astronomer, after whom the later spacecraft would be named, found 4 more Saturnian moons between 1671 and 1684. Slowly, the Saturnian system grew richer and more complex in the scientific imagination. But Titan, the largest of these moons, remained stubbornly featureless in every telescope that studied it. Other moons could eventually be measured, their brightness compared, their orbital periods refined. Titan, however, offered nothing beyond its steady glow and its faithful orbit around Saturn for nearly 300 years. That was all anyone knew. Titan was a large moon. It orbited Saturn, it reflected sunlight, and it kept whatever secrets it held entirely to itself. The first true breakthrough came not through a larger telescope or a closer observation of Titan's surface, but through a technique that analyzed the light passing through its atmosphere. In 1944, the Dutch-American astronomer Gerard Kuiper, working at the McDonnell Observatory in Texas, used a spectrograph to study the light reflected from Titan. A spectrograph separates light into its component wavelengths, revealing the chemical fingerprints of whatever substances that light has passed through. When Kuiper examined Titan's spectrum, he found something that no one had detected around any other moon in the solar system: the unmistakable absorption signature of methane gas. This was a remarkable finding. Methane absorption meant that Titan possessed an atmosphere substantial enough to leave a detectable imprint on reflected sunlight. No other moon was known to have such a thing. Earth's moon had no atmosphere. The moons of Jupiter showed no atmospheric signatures at the time. Titan stood alone as the only known satellite with a real, measurable gaseous envelope surrounding it. Kuiper's discovery transformed Titan from a point of light into a world with atmospheric chemistry. Scientists immediately began to wonder what else might be present in that atmosphere, how thick it might be, what conditions might exist at the surface, and whether the methane was accompanied by other gases. But the technology of the 1940s could answer none of these questions definitively. Titan was simply too far away and too small in even the best telescopes for detailed atmospheric study. Over the following decades, theoretical work attempted to fill in the gaps. Scientists proposed models for Titan's atmosphere based on what was known about methane, about temperatures at Saturn's distance from the Sun, and about atmospheric physics. Some models predicted a thin atmosphere, perhaps only a trace of methane clinging to an icy surface. Others predicted something thicker, perhaps dense enough to support weather or even clouds. Without direct measurements, these remained educated guesses, and the guesses varied widely. The first opportunity for direct investigation came with the Voyager missions. In 1980, Voyager 1 flew past Saturn and was deliberately targeted to pass close to Titan. Scientists had prioritized the encounter specifically because of Titan's known atmosphere. The hope was that Voyager's instruments, far more capable than any Earth-based telescope, would finally reveal what lay beneath the haze. What Voyager 1 found confirmed the most optimistic models and surprised even those who had predicted a substantial atmosphere. Titan's atmosphere was not thin. It was dense, extraordinarily dense. The spacecraft's instruments revealed an atmosphere composed primarily of nitrogen, with methane as a significant secondary component, and a surface pressure approximately 1.5 times that of Earth at sea level. Titan was not merely a moon with traces of gas. It was a world wrapped in a nitrogen atmosphere thicker than Earth's own. But Voyager 1 also delivered a profound disappointment. Its cameras, designed to capture visible light images, could not see through the haze. Titan's atmosphere contained layers of organic aerosols, tiny particles created by ultraviolet sunlight breaking apart methane and nitrogen molecules high in the atmosphere. These particles formed a photochemical smog so thick, so uniformly opaque, that Voyager's images showed nothing but a smooth, featureless orange sphere. No surface features, no clouds, no terrain, just haze. The scientific data was extraordinary. Voyager confirmed that Titan had the densest atmosphere of any moon, that its atmosphere was nitrogen-dominated, like Earth's, and that complex organic chemistry was occurring in its upper layers. Temperature measurements indicated that the surface was brutally cold, approximately -179 degrees Celsius, placing it near the triple point of methane, the temperature and pressure at which methane can exist as solid, liquid, or gas. This raised an intriguing possibility. If methane could exist as liquid at Titan's surface, then perhaps it did. Perhaps Titan had seas, lakes, or rainfall, not of water, but of liquid methane and ethane. It was a tantalizing thought, a world with a weather cycle, a world with liquid on its surface, but Voyager could not confirm it. The haze was impenetrable and the spacecraft was already speeding onward, its trajectory carrying it away from Saturn and toward the outer solar system. Voyager 2 arrived at Saturn in 1981, but its encounter geometry did not include a close Titan flyby. It added useful measurements of the Saturnian system, but Titan's surface remained unseen. After both Voyager spacecraft departed, scientists were left with an extraordinary puzzle. They knew Titan had a thick nitrogen atmosphere. They knew it had methane. They knew organic chemistry was happening. They suspected liquid might exist on the surface, and they had absolutely no way to see whether any of it was true. Titan had revealed just enough to be irresistible, and now, to learn anything more, humanity would have to go back. The desire to return to Titan began almost immediately after Voyager departed. Scientists across multiple space agencies recognized that answering the questions Voyager had raised would require more than a brief flyby. It would require a spacecraft capable of orbiting Saturn for years, studying its moons from multiple angles, peering through Titan's haze, with instruments Voyager never carried, and most ambitiously of all, landing something on Titan's surface. The idea took shape gradually through the 1980s. The European Space Agency and the American National Aeronautics and Space Administration, NASA, began discussing a joint mission that would combine their respective strengths. NASA would build an orbiter, a large and sophisticated spacecraft designed to circle Saturn and conduct repeated close passes of its moons. The European Space Agency would build a probe, a small descent vehicle designed to detach from the orbiter, enter Titan's atmosphere, and descend all the way to the surface, measuring everything it could along the way. The orbiter was named Cassini, after Giovanni Domenico Cassini, the astronomer who had discovered 4 of Saturn's moons and first observed the prominent gap in Saturn's rings that still bears his name. The probe was named Huygens, after Christian Huygens, the very astronomer who had first noticed Titan as a point of light Saturn more than 3 centuries earlier. Together, they became the Cassini-Huygens mission, one of the most ambitious planetary exploration efforts ever undertaken. Building Cassini-Huygens was an enormous undertaking. The orbiter alone was one of the largest and most complex interplanetary spacecraft ever constructed. It carried 12 scientific instruments designed to study Saturn, its rings, its magnetosphere, and its moons in unprecedented detail. Among those instruments were tools specifically designed with Titan in mind, a radar system capable of penetrating Titan's haze and mapping the surface below, an infrared spectrometer that could peer through atmospheric window wavelengths where the haze was partially transparent, an imaging system equipped with filters chosen to see through the upper atmosphere at specific near-infrared wavelengths. For the first time, scientists would have instruments designed not to look at Titan's haze, but through it. The Huygens probe, though far smaller, was no less remarkable. It was designed to survive entry into Titan's atmosphere at tremendous speed, deploy a series of parachutes, and then descend slowly through the entire atmospheric column, measuring temperature, pressure, wind speed, chemical composition, and taking images as it fell. The descent was expected to take approximately 2.5 hours, assuming the parachute systems functioned correctly and the atmosphere behaved as models predicted. If all went well, Huygens would eventually reach the surface, and depending on what that surface turned out to be, solid ground, liquid, or something in between, it might continue transmitting for a short time after touchdown. No one knew what Huygens would find when it arrived. Some scientists predicted the probe would splash down into a global ocean of liquid methane and ethane. Others believed it would land on a frozen surface of water ice. Some proposed a surface covered in thick, organic sludge, the accumulated products of billions of years of atmospheric chemistry raining down from above. The uncertainty was one of the mission's greatest challenges. Engineers had to design a probe that could survive landing on solid ice, floating on liquid hydrocarbons, or sinking into organic mud. And they could not know which scenario they were designing for until the probe actually arrived. Cassini-Huygens launched on the 15th of October 1997 from Cape Canaveral in Florida atop a Titan I rocket. The spacecraft was too heavy and Saturn too distant for a direct flight. Instead, mission planners designed a complex trajectory that used gravitational assists from Venus, Earth, and Jupiter to gradually accelerate the spacecraft to the velocity needed to reach Saturn. This meant that Cassini-Huygens would not travel in a straight line. It would loop through the inner solar system twice, swinging past Venus in April 1998 and again in June 1999, then past Earth in August 1999, and finally past Jupiter in December 2000, before arcing outward towards Saturn. The journey took nearly 7 years. During those years, the spacecraft was mostly silent, its instruments dormant, its systems in a carefully managed state of minimal activity as it crossed the vast emptiness between planets. Occasionally, mission controllers would wake instruments for calibration or testing, and the Jupiter flyby provided an opportunity to observe the Jovian system and verify that everything was functioning correctly. But for most of the voyage, Cassini-Huygens drifted quietly, a human-built machine carrying the combined hopes of 2 space agencies across billions of kilometers of empty space. On the 1st of July, 2004, Cassini arrived at Saturn. The spacecraft fired its main engine for 96 minutes, a precisely calculated burn that slowed it just enough to be captured by Saturn's gravity. It was a critical maneuver. If the burn had been too short, Cassini would have sailed past Saturn and continued into deep space with no possibility of return. If the burn had been too long, the spacecraft might have entered an orbit too close to the planet. The margin was narrow, and mission controllers on Earth could do nothing but wait. The signal from Saturn took more than an hour to reach Earth. By the time controllers received confirmation that the burn had begun, it had already been underway for more than an hour. By the time they learned it had succeeded, Cassini was already orbiting Saturn. The first images sent back were breathtaking. Saturn's rings appeared in extraordinary detail, with structures visible that no telescope on Earth or in orbit around Earth had ever resolved. The planet itself displayed subtle bands of cloud in shades of gold and cream, and among the moons visible in those early images one stood out, a hazy orange sphere, partially illuminated by sunlight filtering through its atmosphere, Titan. But Cassini's work at Titan would be methodical, not rushed. The mission was designed to last at least 4 years in orbit, during which the spacecraft would make dozens of close flybys of Titan, each one from a slightly different angle, each one with instruments configured for specific observations. Over time, the data from these flybys would build a comprehensive portrait of Titan that no single flyby could provide. The first close Titan flyby occurred on the 26th of October, 2004. Cassini passed within approximately 1,200 kilometers of Titan's surface, and for the first time, its radar pierced the haze. The radar worked by sending microwave pulses downward toward the surface and measuring the echoes that bounced back. Unlike visible light, microwaves passed through Titan's atmosphere without significant obstruction, revealing the surface beneath. Not a featureless plain or a global ocean. It was terrain, complex, varied, textured terrain. Scientists saw areas that appeared smooth, suggesting liquid or fine sediment. They saw areas that appeared rough, suggesting solid surfaces with topographic features. They saw linear structures that might be ridges, channels, or geological formations. After a single pass, the picture was fragmented, like seeing a country through a narrow window on a fast-moving train. But even those fragments were extraordinary. Titan had a surface, and that surface was geologically diverse. Cassini's infrared instruments added another layer of information. By observing Titan at wavelengths, where the atmosphere was partially transparent, these instruments could detect brightness variations on the surface. Bright regions suggested different compositions from dark regions. Large dark areas near the equator were noted, along with brighter areas at higher latitudes. The surface was not uniform. Something was creating distinct regions of different albedo, different reflectivity, and scientists began speculating about what those regions might represent. In December of 2004, Cassini released the Huygens probe. Huygens separated from the orbiter on the 25th of December and began a 20-day coast toward Titan, unpowered, following a trajectory calculated months in advance. Cassini, meanwhile, maneuvered into position to serve as a communications relay. Huygens had no ability to transmit directly to Earth. Its signal was too weak and Titan too distant. Instead, it would transmit upward to Cassini, which would record the data and forward it to Earth. On the 14th of January, 2005, Huygens entered Titan's atmosphere. The probe struck the upper atmosphere at a speed of approximately 6 kilometers per second. A heat shield absorbed the tremendous energy of entry, and as the probe decelerated, it experienced forces several times the strength of Earth's gravity. Within minutes, the heat shield had done its work, and a drogue parachute deployed, pulling away the shield and releasing the main parachute. Huygens began its slow descent through the thickest atmosphere of any moon in the solar system. For the next 2 hours and 27 minutes, Huygens fell through Titan's sky, and every second of that descent produced data that scientists on Earth had waited decades to receive. The probe measured temperature and pressure continuously. At the top of the atmosphere, conditions were thin and bitterly cold. As Huygens descended, the atmosphere thickened. Pressure increased steadily. Temperature dropped initially, reaching a minimum in the stratosphere, then began to rise slightly in the lower atmosphere as the increasing pressure warmed the gas. By the time Huygens approached the surface, the temperature had settled near -179 degrees Celsius, and the pressure was approximately 1.5 times sea level pressure on Earth. The atmosphere was thick enough that Huygens descended the final portion of its journey using only a small stabilizer parachute, the main parachute having been released earlier to prevent the descent from taking too long and exhausting the probe's batteries before reaching the surface. As it fell, Huygens sampled the atmosphere directly. Its gas chromatograph and mass spectrometer identified nitrogen as the dominant gas, confirming Voyager's finding. Methane was present throughout, increasing in concentration closer to the surface. But the instruments also detected traces of other gases and complex organic molecules, products of the photochemical reactions occurring high above. The atmosphere was not simply nitrogen and methane. It was a chemical factory, producing a continuous supply of organic compounds that slowly drifted downward through the haze layers. The descent imager, spectral radiometer, one of Huygens' most anticipated instruments, captured images during the descent. At high altitude, the view showed only haze. As the probe descended below the main haze layers, features began to emerge. The images revealed a landscape that stunned the science team. Bright highlands were cut by dark, branching channels that converged into larger drainage networks. The pattern was unmistakable. These were river valleys, not rivers of water, but channels carved by flowing liquid, almost certainly liquid methane, into the frozen surface of Titan. The channels flowed from brighter elevated terrain toward darker lowland areas. The branching patterns resembled dendritic drainage networks on Earth, the kind of patterns formed when rainfall collects on a surface and flows downhill, merging into progressively larger streams. The implication was extraordinary. It rained on Titan. Liquid methane fell from the sky, collected on the surface, flowed downhill, carved channels, and drained into lower areas, just as water does on Earth. As Huygens continued its descent, the surface came into sharper focus. The final images before landing showed a flat, dark plain scattered with rounded objects. These were small, rounded pebbles or cobbles, roughly 10 to 15 centimeters across, made of water ice. Their rounded shapes suggested they had been tumbled and smoothed by flowing liquid, much as river stones on Earth are rounded by water. Huygens was descending toward what appeared to be a dry riverbed or floodplain. At approximately 11:38 UTCT, Huygens touched down on Titan's surface. The impact was gentle, consistent with landing on a surface that was not hard rock, but something softer. The penetrometer, an instrument designed to measure the mechanical properties of the surface on impact, indicated a thin crust overlying a softer material, perhaps frozen hydrocarbon sediment with the consistency of wet sand or compacted snow. Huygens had landed on solid ground, but ground that was not entirely rigid. After landing, the probe continued to transmit data. Its instruments detected a brief increase in methane concentration near the surface, immediately after impact, suggesting that the landing may have warmed the surface slightly, causing methane to evaporate from the ground. This indicated that the surface material contained methane, either frozen within it or adsorbed onto its grains. Titan's surface was not merely cold. It was saturated with the same substance that fell from its sky. Huygens transmitted from the surface for approximately 72 minutes after touchdown before its batteries were exhausted and its relay link with Cassini passed out of range. In total, the probe had operated for roughly 3.5 hours from atmospheric entry to final signal. It returned 350 images, atmospheric profiles, wind measurements, surface data, and chemical analyses that would take years to fully interpret. It was the most distant landing ever accomplished by a human-built spacecraft, and it had revealed a world far more complex, far more active, and far more Earth-like in its processes than anyone had confidently predicted. With Huygens on the surface and Cassini continuing to orbit, the real exploration of Titan was only beginning. To understand Titan, one must first understand the atmosphere that surrounds it, not as a thin shell of gas, not as a simple envelope, but as a deep, active, layered system that defines nearly everything about the world beneath it. Titan's atmosphere is not merely a feature of the Moon. In many ways, the atmosphere is the story. It is the reason Titan remained hidden for so long, the reason its surface chemistry is so complex, and the reason scientists compare this frozen moon to a version of Earth that has been slowed down, cooled, and translated into an entirely different chemical language. The atmosphere begins at the surface, where pressure reaches approximately 1.5 bars. 1 bar is roughly the atmospheric pressure at sea level on Earth, so Titan's surface pressure is about 50% greater. This is a remarkable figure for a moon. To find comparable surface pressure anywhere else in the solar system, one must look not at moons, but at planets. Venus has a surface pressure roughly 90 times that of Earth. Mars has a surface pressure less than 1% of Earth's. Titan, a moon smaller than Mars, has a surface pressure closer to Earth's than either of those planets. It is an anomaly. A world that by every expectation should have lost its atmosphere long ago, but has instead maintained one of the thickest and most chemically active atmospheres in the solar system. The primary constituent is nitrogen. Approximately 95% of Titan's atmosphere is molecular nitrogen, the same gas that makes up roughly 78% of Earth's atmosphere. This is not a coincidence in the sense that the same processes created both atmospheres, but it is a profound similarity. Nitrogen is a relatively inert gas under most conditions, and its dominance in both atmospheres creates a shared foundation that influences everything from pressure to heat distribution to the behavior of other gases within the mixture. The second most abundant gas is methane, which constitutes approximately 5% of the atmosphere near the surface, with the proportion varying at different altitudes and latitudes. Methane is to Titan what water vapor is to Earth, a substance that exists in multiple phases, cycles between surface and atmosphere, and drives weather. On Earth, water evaporates from oceans, rises, condenses into clouds, and falls as rain. On Titan, methane evaporates from lakes and seas, rises through the cold atmosphere, condenses into clouds, and falls as methane rain. The parallel is not metaphorical. It is physical. The same thermodynamic principles that govern Earth's water cycle govern Titan's methane cycle, operating at far lower temperatures but following identical laws. Beyond nitrogen and methane, Titan's atmosphere contains a rich assortment of trace gases, many of which are products of atmospheric chemistry rather than original constituents. Ethane, propane, acetylene, hydrogen cyanide, carbon dioxide in traces, and numerous other organic molecules have been detected at various altitudes. These are not present because they were delivered to Titan during its formation. They are present because the atmosphere continuously manufactures them. The chemistry begins high above the surface, in the upper atmosphere, where solar ultraviolet radiation and energetic particles from Saturn's magnetospheres strike nitrogen and methane molecules with enough energy to break them apart. When a methane molecule is dissociated, its fragments, individual carbon and hydrogen atoms, and small molecular radicals become available for recombination. When a nitrogen molecule is broken, its atoms can participate in entirely new chemical pathways. The resulting reactions produce a cascade of increasingly complex molecules, starting with simple two-carbon compounds like ethane and acetylene, and progressing through longer carbon chains and nitrogen, bearing organics to molecules of considerable complexity. This process is called photochemistry, and on Titan, it operates on a scale found nowhere else among the moons of our solar system. The products of these reactions do not remain as gases indefinitely. Many of them condense at the low temperatures found in Titan's stratosphere, forming tiny solid particles. These particles are called aerosols, and collectively, they constitute the haze that gives Titan its characteristic orange color and renders its surface invisible at most wavelengths of light. The aerosols are often referred to informally as tholins, a term coined by the astronomer Carl Sagan and the chemist Bishun Kare in the 1970s to describe the complex organic solids produced when energy sources act on mixtures of nitrogen and methane. Sagan and Kare created tholins in laboratory experiments by exposing nitrogen-methane gas mixtures to electrical discharges and ultraviolet light. The resulting material was a reddish, brown solid composed of a complex mixture of organic molecules, including amino acids and other compounds of prebiotic interest. When scientists later observed Titan's orange haze, the connection was immediately apparent. The haze particles were likely similar in composition to the tholins produced in the laboratory, complex organic solids created by photochemistry acting on the same gases that Sagan and Kare had used. The haze is not a single uniform layer. It has structure. Observations from Voyager, ground-based telescopes, and Cassini have revealed that Titan's haze consists of multiple layers extending from the surface to altitudes exceeding 300 kilometers. The main haze layer sits in the stratosphere, between roughly 100 and 300 kilometers above the surface. But a detached haze layer has been observed at even higher altitudes, and haze particles extend all the way down to the surface, giving Titan's lower atmosphere a perpetual murky quality. The vertical structure of the atmosphere itself follows a pattern that planetary scientists describe using the same terminology applied to Earth's atmosphere, because the physical principles are the same. Closest to the surface is the troposphere, the layer where temperature generally decreases with altitude and where weather occurs. On Titan, the troposphere extends from the surface to an altitude of approximately 40 to 44 kilometers. At the surface, the temperature is approximately 94 Kelvin, or minus 179 degrees Celsius. Temperature decreases with altitude through the troposphere, reaching a minimum of roughly 71 Kelvin at the tropopause, the boundary between the troposphere and the layer above. Above the tropopause lies the stratosphere, where temperature increases with altitude due to absorption of solar radiation by the haze particles and certain gases. This temperature inversion creates a stable layer that suppresses vertical mixing, much as Earth's stratosphere does. Titan's stratosphere extends to roughly 300 kilometers above the surface, and within it, temperatures gradually rise back toward 170 Kelvin or higher. The haze production occurs primarily within and above this layer. Above the stratosphere lies the mesosphere, where temperatures decrease again, and above that, the thermosphere, where temperatures rise due to direct absorption of extreme ultraviolet radiation and the interaction of energetic particles with atmospheric gases. The thermosphere of Titan extends to very high altitudes, and its upper reaches blend into the exosphere, the region where individual molecules can escape into space if they have sufficient velocity. This atmospheric structure matters because it governs how energy, chemistry, and material move through the system. Photochemistry occurs in the upper atmosphere. The products drift downward through the stratosphere, where many condense into haze particles. The haze particles continue to settle, absorbing and scattering sunlight as they descend, gradually making their way through the troposphere toward the surface. By the time these particles reach the ground, they have been falling for years, or even decades, accumulating on the surface as a layer of organic sediment. Scientists have estimated the rate at which organic material is deposited on Titan's surface by the continuous rain of haze particles. The figures vary depending on the model, but most estimates suggest that over the age of the solar system, the accumulated organic deposits could form a layer meters to tens of meters thick across the entire surface. Some of this material dissolves in liquid methane and ethane. Some of it is carried by rivers and deposited in lowlands. Some of it forms the dark material that covers much of Titan's equatorial regions. The atmosphere, through its photochemistry, is literally building the surface geology of Titan, one tiny particle at a time. The methane that drives this chemistry poses a fundamental puzzle. Methane is continuously destroyed by photochemistry in the upper atmosphere. The products of that destruction, ethane, acetylene, more complex organics, do not convert back to methane under Titan's conditions. This means the atmosphere's methane supply is being irreversibly consumed. At current rates of destruction, the methane in Titan's atmosphere should be entirely depleted within roughly 10 to 30 million years. Yet Titan clearly has methane. Its atmosphere is rich with it. Its surface has methane lakes and seas. Something must be replenishing the supply. The source of Titan's methane remains one of the major unsolved questions about this moon. Hypotheses have been proposed. One is that methane is stored in a subsurface reservoir, perhaps as methane clathrates, crystalline structures in which methane molecules are trapped within cages of water ice. These clathrates could release methane episodically, driven by internal heating or geological activity, resupplying the atmosphere over time. Another possibility is that cryovolcanism, volcanic-like eruptions of volatile materials rather than molten rock, occasionally vents methane from the interior to the surface and atmosphere. A third possibility involves slow outgassing from Titan's interior through geological processes that have not yet been directly observed. None of these hypotheses has been confirmed. Cassini found possible evidence of cryovolcanic features on Titan's surface, but the interpretation remains debated. The presence of large quantities of methane in the polar seas suggests a substantial surface and near-surface reservoir, but whether this reservoir is being actively replenished or simply represents a slowly depleting remnant is not yet clear. The methane question is intimately connected to questions about Titan's geological activity, its internal structure, and its long-term atmospheric evolution, and answering it may require future missions capable of studying the subsurface directly. The winds that move through this atmosphere are generally gentle near the surface, typically less than 1 meter per second at ground level, based on Huygens measurements during descent. This is barely a breeze by Earth standards. But higher in the atmosphere, winds become significantly stronger. In the stratosphere, a phenomenon known as superrotation occurs, in which the atmosphere at certain altitudes rotates faster than the solid body of Titan itself. This superrotation creates strong eastward winds at high altitudes, reaching speeds of over 100 meters per second near the equator in the upper stratosphere. The phenomenon is similar to the superrotation observed in the atmosphere of Venus, where the upper atmosphere circles the planet far faster than the planet rotates. At lower altitudes, within the troposphere where weather occurs, winds are more moderate but still capable of shaping the surface. Near the equator, prevailing surface winds blow predominantly from the east in most seasons, though the wind direction can reverse during equinox periods when the sun crosses Titan's equator. These winds are responsible for shaping Titan's vast equatorial dune fields, transporting fine organic particles across the surface and building them into the long parallel ridges that Cassini's radar revealed, stretching across thousands of kilometers of low-latitude terrain. Titan's atmosphere also exhibits seasonal variation, a consequence of Saturn's axial tilt. Saturn is tilted approximately 26.5 degrees relative to its orbital plane, and since Titan orbits within Saturn's equatorial plane, Titan experiences the same seasons as Saturn. However, Saturn's orbital period is approximately 29.5 Earth years, meaning each season on Titan lasts roughly 7 Earth years. During Cassini's 13 years in the Saturn system, scientists were able to observe Titan transition from northern winter through spring and into early summer, watching as cloud patterns shifted, haze distributions changed, and atmospheric circulation reorganized. One of the most significant seasonal changes involves the polar vortex. During winter at each pole, the atmosphere above the pole cools and subsides, creating a concentrated region of cold, descending air enriched with photochemical products from higher altitudes. Cassini observed a dramatic vortex forming over Titan's south pole as southern autumn approached, with a distinct cloud of condensed gases appearing at high altitude within the vortex. This polar vortex structure is analogous to polar vortices on Earth, though the chemistry involved is entirely different. The atmosphere of Titan is, in a sense, an enormous chemical laboratory operating continuously in the cold outer solar system. It takes simple ingredients, nitrogen and methane, and through the energy provided by distant sunlight and Saturn's magnetosphere, it produces an extraordinary range of complex organic molecules. These molecules drift downward, building the surface, filling the seas with dissolved compounds, and creating an environment of organic richness that is unmatched anywhere else in the solar system outside of Earth. This atmospheric chemistry is one of the reasons scientists consider Titan one of the most important targets for future exploration. The organic molecules produced in Titan's atmosphere include many of the same building blocks that are thought to have been important in the origin of life on Earth, including hydrogen cyanide, which can polymerize into compounds of biological relevance, and various nitrile compounds that participate in prebiotic chemistry. Titan's atmosphere is not producing life. The temperatures are far too low, and liquid water, considered essential for life as we know it, is not available at the surface. But the atmosphere may be producing the raw materials of life, the chemical precursors that, given the right conditions, might begin the long chain of reactions leading toward biology. Understanding Titan's atmosphere is therefore not only a matter of planetary science. It is a window into the chemistry that may have preceded life itself, frozen in time and operating at a scale that no laboratory on Earth could replicate. The atmosphere wraps Titan in complexity, in mystery, and in a quiet, continuous process of creation that has been running for billions of years. Of all the discoveries made at Titan, none captured the imagination of scientists and the public more completely than the confirmation that liquid exists on its surface, not trapped beneath ice, not inferred from chemistry. Liquid, sitting openly under the sky, pooling in basins, filling depressions, forming bodies that can only be described as lakes and seas. Titan became the only world in the solar system, other than Earth, known to have stable bodies of liquid on its surface at the present day. And while those bodies are not water, while they are composed of substances that on Earth exist only as gases, their presence transforms Titan from an interesting moon into something far more profound. A world with a liquid cycle, a world with hydrology. The first definitive evidence came from Cassini's radar. During repeated flybys of Titan's polar regions, the spacecraft's synthetic aperture radar returned images that showed vast dark areas near the North Pole. In radar imagery, smooth surfaces appear dark because they reflect the radar signal away from the spacecraft like a mirror, returning very little energy to the receiver. Rough surfaces, by contrast, scatter the signal in many directions, and some of that scattered energy returns to the spacecraft, making rough terrain appear bright. The dark regions near Titan's North Pole were among the smoothest surfaces the radar had ever measured on any planetary body. They were flat, extraordinarily, almost impossibly flat. The most natural explanation was liquid. A surface of liquid methane or ethane would be smooth enough to produce exactly the radar signature Cassini observed. The largest of these dark regions was enormous. It covered an area of roughly 380,000 square kilometers, larger than the Caspian Sea on Earth, the largest enclosed body of water on our planet. Scientists named it Kraken Mare, after the legendary sea creature of Scandinavian mythology. It was not the only sea. A second large body, Ligeia Mare, covered approximately 126,000 square kilometers. A third, Punga Mare, was smaller but still substantial. Together with dozens of smaller lakes scattered across the North Polar region, these bodies of liquid formed a hydrological system of remarkable scale. The radar data revealed not only the extent of these seas, but also details about their edges. Kraken Mare had a complex shoreline with bays, inlets, peninsulas, and what appeared to be islands. Channels connected different sections of the sea, and in some areas, the shoreline showed features that resembled flooded river valleys, as though liquid had risen and filled low-lying terrain. Ligeia Mare had a smoother, more rounded outline, but it too showed channels feeding into it from the surrounding highlands. The seas were not isolated pools. They were connected to the broader landscape through drainage networks fed by rivers that carried liquid from higher elevations down into the basins where the seas collected. Determining the composition of these seas required more than radar imagery. Cassini carried a visual and and infrared mapping spectrometer, known as VIMS, which could observe Titan's surface through narrow atmospheric windows in the near-infrared spectrum. By analyzing the sunlight reflected from the surface of Titan's lakes and seas, scientists could identify the spectral signatures of the liquids. The results indicated that the seas were composed primarily of methane and ethane, with methane likely dominating in some bodies and ethane in others. Dissolved nitrogen was also present, as nitrogen from the atmosphere would naturally dissolve into the liquid hydrocarbons at Titan's surface temperatures and pressures. The depth of the seas proved more difficult to measure, but Cassini's radar provided some answers. In certain flybys, the radar signal penetrated the liquid surface of Ligeia Mare and reflected off the sea floor beneath. By measuring the time delay between the surface echo and the bottom echo, scientists calculated that Ligeia Mare reached depths of approximately 160 meters in some locations. For Kraken Mare, the radar could not detect a bottom echo in most areas, suggesting either that the sea was too deep for the signal to penetrate and return, or that the liquid absorbed too much of the radar energy. Estimates based on the available data suggested that Kraken Mare might reach depths of 300 meters or more in its deepest regions. These are substantial bodies of liquid, not puddles, not thin films. Deep seas with complex bathymetry, coastlines shaped by geological processes, and connections to river systems that extend far inland. The total volume of liquid hydrocarbons on Titan's surface has been estimated at several tens of thousands of cubic kilometers. If all the liquid methane and ethane on Titan were gathered together, it would represent a quantity of hydrocarbon that dwarfs the known oil and natural gas reserves of Earth many times over. This comparison is scientifically irrelevant in practical terms, but it illustrates the scale of what exists on Titan's surface. The distribution of the seas revealed an unexpected asymmetry. Nearly all of Titan's large lakes and seas are concentrated in the northern hemisphere. The South Polar region, while not entirely dry, has far fewer and smaller liquid bodies. Ontario Lacus, the largest confirmed lake in the southern hemisphere, covers an area of roughly 15,000 square kilometers, comparable to Lake Ontario on Earth, which inspired its name. But it is far smaller than the Great Northern Seas, and the overall liquid inventory in the south is a fraction of what exists in the north. Scientists have proposed several explanations for this asymmetry. One hypothesis involves the shape of Saturn's orbit around the Sun. Saturn's orbit is slightly elliptical, meaning that at certain points in its orbit, Saturn and its moons are closer to the Sun and receive slightly more solar energy. Currently, southern summers on Titan coincide with the part of Saturn's orbit that brings it closer to the Sun, making southern summers slightly warmer and longer than northern summers. This could cause more evaporation from southern liquid bodies and transport of methane vapor toward the cooler north, where it condenses and accumulates. Over thousands of years, this asymmetry could shift the bulk of Titan's surface liquid toward the northern hemisphere. Another hypothesis involves topography. If the northern polar regions are lower in elevations than the southern polar regions, liquid would naturally drain and collect in the north. Cassini's radar altimetry data provided some support for this idea, showing that the northern polar terrain is generally lower than the southern polar terrain. Though the measurements were not comprehensive enough to fully confirm the hypothesis, the truth may involve a combination of both factors, and possibly others not yet identified. The distribution of liquid on Titan is one of many questions that remain open, awaiting future missions with more capable instruments. The lakes of Titan are not all the same. Some appear to be filled with liquid, others appear to be partially filled or seasonal, their levels changing over time. Some appear to be entirely dry, their basins empty, marked only by the distinctive dark, flat signature of a smooth surface that may be covered by a residue of heavier hydrocarbons left behind after lighter methane evaporated. These dry lake beds suggest that Titan's hydrological cycle is not static. Lakes fill and empty. Liquid moves. The balance between evaporation and rainfall shifts with the seasons. Cassini observed evidence of this seasonal change directly. Over the course of its 13-year mission in the Saturn system, the spacecraft watched as subtle changes occurred in Titan's polar regions. Features that had appeared dark in early flybys became slightly brighter in later ones, or vice versa. Near the South Pole, Ontario Lacus appeared to shrink slightly between observations made years apart, consistent with evaporation during the approach of southern autumn and winter, when that hemisphere would receive less sunlight and the atmospheric dynamics would shift. One of the most striking observations involved a feature that appeared temporarily in the southern hemisphere. During a flyby in 2009, Cassini's radar detected a large dark patch in a region where no lake had been seen before. The feature appeared to be a thin layer of liquid, possibly deposited by recent rainfall. In subsequent flybys, the feature had faded, consistent with evaporation. Scientists interpreted this as possible evidence of a faint rainstorm, a transient event that deposited liquid on the surface, which then slowly evaporated back into the atmosphere. This brings us to the most remarkable aspect of Titan's liquid cycle, the rain. Methane rain on Titan is not a continuous drizzle. Climate models and Cassini observations suggest that rainfall on Titan is infrequent but potentially intense. At any given time, much of Titan's surface may be dry, experiencing long intervals between precipitation events. But when rain does fall, it may come in heavy downpours, releasing large quantities of liquid methane that flow across the surface, carve channels, fill basins, and reshape the landscape before slowly evaporating back into the atmosphere. The mechanics of this rainfall are governed by the same physics that governs rainfall on Earth, adapted to Titan's conditions. Methane evaporates from lakes, seas, and moist ground. The vapor rises through the troposphere, where temperatures decrease with altitude. At sufficient altitude, the methane vapor reaches its saturation point and condenses, forming cloud droplets. These droplets grow, coalesce, and eventually become heavy enough to fall as rain. The drops themselves would be different from raindrops on Earth. In Titan's low gravity, roughly 1/7 of Earth's gravity, and thick atmosphere, methane raindrops would fall slowly, reaching terminal velocities far lower than raindrops on Earth. They would also be larger, because the lower gravity allows larger drops to form before being broken apart by air resistance. A methane raindrop on Titan might be several times the size of a typical terrestrial raindrop, falling gently through the thick orange atmosphere at perhaps 1.5 meters per second, roughly the speed of a leisurely walk. The image this creates is extraordinary. Imagine standing on Titan's surface during a rainfall event. The sky above is a deep orange haze, dimly lit by sunlight that has traveled nearly 1.5 billion kilometers. The air is thick and cold, pressing against you with a pressure greater than sea level on Earth. And from that sky, large, slow drops of liquid methane fall, drifting downward almost lazily, landing on the frozen ground and beginning to flow. The drops merge into trickles, the trickles into streams, the streams into rivers, all flowing downhill toward the dark, still seas that wait in the polar lowlands. Cassini observed methane clouds on Titan directly. Cloud activity was concentrated near the poles initially, consistent with seasonal weather patterns. As Titan's seasons shifted during the Cassini mission, clouds were observed at different latitudes, sometimes appearing dramatically in equatorial regions where they had not been seen before. In 2010, Cassini and ground-based observers detected a large storm system near Titan's equator with extensive cloud cover that appeared suddenly and then dissipated over a period of weeks. This equatorial storm was particularly significant because it occurred in a region covered by vast dune fields, areas that appeared to be among the driest on Titan. The storm suggested that even these arid equatorial regions occasionally receive precipitation, providing the moisture needed to maintain the cycle. The rivers that carry this rainfall across Titan's surface were among the most visually striking features revealed by Cassini. The spacecraft's radar mapped numerous channel networks across the Moon, with some channels extending for hundreds of kilometers. These channels show the classic branching pattern of dendritic drainage, where smaller tributaries merge into larger channels that eventually empty into a sea or lake. The pattern is nearly identical to river drainage systems on Earth because the physics of flowing liquid on a surface is the same, regardless of whether the liquid is water or methane. One particularly dramatic channel system was observed near the northern seas. A long, narrow feature, bright in some radar images and dark in others, depending on viewing angle and liquid content, wound its way from the highlands south of Ligeia Mare northward into the sea itself. The channel, informally compared to a miniature version of the Nile, extended for more than 400 kilometers. Its width was narrow, just a few kilometers at most, but its length and sinuosity demonstrated that sustained flow had carved a path through Titan's surface over extended periods. The material that composes Titan's surface and through which these rivers cut is primarily water ice. At Titan's surface temperatures, water ice is as hard as granite and plays the same structural role that silicate rock plays on Earth. The rivers are not cutting through soft material. They are eroding frozen ice, using the same processes of dissolution, abrasion, and hydraulic action that terrestrial rivers use to erode rock. The timescales may be different, the chemistry is entirely different, but the geomorphology is recognizably the same. In some regions, Cassini's radar revealed features that resembled canyons. A particularly notable set of channels near Ligeia Mare showed steep-walled canyons with depths estimated at several hundred meters and widths of less than a kilometer. These channels were filled with liquid at the time of observation, appearing as dark lines in the radar data. Their narrow width and considerable depth suggested that powerful, sustained flow had carved deep into the icy surface, creating landforms that might resemble slot canyons on Earth. The rivers, lakes, and seas of Titan together form a coherent hydrological system. Methane evaporates from the seas. It enters the atmosphere, is transported by winds, condenses into clouds, and falls as rain. The rain collects on the surface and flows through rivers back toward the seas. Along the way, it erodes the surface, transports sediment, and deposits material in deltas and lowlands. The cycle is continuous, though not uniform. Different regions experience different rainfall amounts. Different seasons bring different weather patterns. The system is dynamic, responsive to orbital mechanics, atmospheric circulation, and the slow evolution of Titan's climate. This hydrological cycle is what makes Titan so compelling to planetary scientists. It is the only place beyond Earth where we can study a complete liquid cycle operating on a planetary surface. The chemistry is different, the temperatures are different, the timescales may be different, but the fundamental processes, evaporation, condensation, precipitation, runoff, erosion, deposition, collection, are the same. Titan provides a natural laboratory for understanding how these processes work, under conditions radically different from Earth. And in doing so, it deepens our understanding of how they work on Earth as well. The seas of Titan are quiet now, as far as we know. No waves have been conclusively detected on their surfaces, though Cassini may have observed faint surface roughening on Punga Mare during a flyby in 2013. that could represent small waves driven by seasonal winds. If waves do form on Titan's seas, they would be slow-moving, gentle swells in the thick atmosphere and low gravity, unlike anything on Earth's oceans. The seas may spend most of their time in near-perfect stillness, their surfaces reflecting the faint diffused glow of a sun that appears as little more than a bright spot in the orange sky. Somewhere on Titan, right now, those seas remain. Krakenmeer stretch across the northern polar region, dark and still. Ligeia sits nearby, its smooth surface hiding depths that Cassini measured but never fully explored. Rivers wait in dry channels for the next rainfall to fill them. The methane cycle turns slowly, governed by seasons that last 7 Earth years, and by orbital mechanics that shift the balance of liquid from one hemisphere to the other, across millennia. It is a world with hydrology, with weather, with landscapes shaped by flowing liquid, and it is a world we have only begun to understand. Beyond the polar seas, beyond the river networks that drain into methane shorelines, Titan's surface reveals an entirely different landscape, one that at first glance seems to belong to a different world altogether. Stretching across the equatorial regions of the Moon, covering an area so vast that it dwarfs any comparable feature on Earth, lie the dune fields of Titan. Long, dark, parallel ridges running east to west for hundreds, and in some cases, over 1,000 kilometers, separated by narrow corridors of brighter terrain, forming patterns so regular and so extensive that, when Cassini's radar first revealed them, scientists immediately recognized them as dunes. Not geological ridges, not tectonic formations. Dunes built by wind, shaped by atmospheric dynamics, and composed of material that had drifted down from the sky above. The discovery of Titan's dunes was one of the most unexpected findings of the Cassini mission. Before the spacecraft arrived, most models of Titan's surface predicted a world dominated by liquid methane. Some models suggested a global ocean. Others suggested extensive swamps or mudflats of organic material. Very few predicted vast dry deserts of wind-shaped sand. Yet the radar data was unambiguous. Across the equatorial band, between roughly 30 degrees north and 30 degrees south latitude, Titan's surface is dominated by these linear dune formations. They cover an estimated 12 to 13% of the Moon's total surface area, making them one of the most extensive dune systems known anywhere in the solar system. On Earth, the most familiar comparison is the longitudinal dunes found in the Sahara Desert and the Namib Desert, where persistent winds create long parallel ridges of sand extending for tens of kilometers. Titan's dunes follow the same physical principles, but operate at a scale that exceeds anything found on Earth. Individual dune ridges on Titan can reach heights estimated at 100 to 150 meters and widths of 1 to 2 kilometers. They are separated by interdune corridors, roughly 1 to 4 kilometers wide, and they extend continuously for distances that can exceed 1,000 kilometers, far longer than any comparable dune on Earth. The material that composes these dunes is not silicate sand. On Titan, the dune grains are organic particles, likely derived from the photochemical haze that forms in the upper atmosphere. These particles, the tholins and related organic solids, produced by the action of ultraviolet light on nitrogen and methane, settle slowly through the atmosphere over years and decades, eventually reaching the surface. Once on the ground, they accumulate and are transported by wind, much as quartz sand is transported by wind on Earth. The particles are thought to be roughly the size of coarse sand grains on Earth, perhaps a few hundred micrometers in diameter, though direct measurement has not been possible. This means that Titan's dunes are built from material manufactured by the atmosphere itself. The photochemistry that creates the orange haze is, in effect, producing the sediment that covers much of the equatorial surface. It is a connection that illustrates how deeply intertwined Titan's atmosphere and surface are. The same process that obscures the surface from view is simultaneously building that surface, grain by grain, over geological time. The orientation of the dunes reveals information about Titan's wind patterns. Cassini's radar observations showed that the dunes generally run in an east-east-west direction, with slight deviations around topographic obstacles, such as elevated terrain or impact craters. When dunes encounter an obstacle, they divert around it, creating patterns that allow scientists to infer the dominant wind direction. That the dunes are shaped by near-surface winds blowing predominantly from the west near the equator. This was initially surprising because global circulation models for Titan predicted easterly surface winds at low latitudes for most of the year. The resolution of this apparent contradiction came through more sophisticated atmospheric modeling. Scientists discovered that while the time-average surface winds at the equator are indeed easterly, brief but powerful westerly wind events occur near the equinox, when Titan's seasons change and the atmospheric circulation pattern reorganizes. These episodic westerly gusts, though short-lived compared to the prevailing easterlies, may carry enough energy to move dune grains and dominate the long-term dune morphology. It is the strong events, not the average conditions, that shape the dunes. This is similar to what happens in some terrestrial desert environments, where rare but intense storms do more geomorphic work than months of gentle prevailing winds. The equatorial concentration of the dunes tells another part of the story. Titan's equatorial region is the driest part of the Moon. The polar regions receive more methane precipitation and host the lakes and seas. The mid-latitudes appear to have more varied terrain with possible evidence of past fluvial activity. But the equator, distant from the polar moisture sources and receiving less precipitation in current climate models, is where organic sediment accumulates and dries sufficiently to be mobilized by wind. The distribution of dunes is therefore a map of Titan's climate, marking the regions where aridity dominates and atmospheric sediment can be reworked by wind rather than being trapped by liquid. Among the dune fields, Cassini identified several named sand seas, regions of especially extensive and continuous dune coverage. The largest of these include Shangri-La, Fensel, Aslan, and Belet, informal names drawn from mythological and literary traditions, as is the convention for Titan's surface features. These sand seas cover areas of hundreds of thousands of square kilometers each, and collectively they represent one of the largest reservoirs of organic material on Titan's surface. The dunes also interact with other surface features in revealing ways. In some areas, dune fields abut mountainous terrain or elevated blocks of crust, and the dunes wrap around these obstacles, providing information about both wind patterns and the three-dimensional structure of the surface. In other areas, dune fields appear to be interrupted by channels or bright terrain that may represent areas where liquid methane has flowed, either washing away dune material or depositing different sediment. These interactions between aeolian and fluvial processes create a surface that is not dominated by any single geological agent, but shaped by the interplay of wind, liquid, atmospheric deposition, and underlying topography. Cassini's radar also revealed that Titan's surface contains mountains, though not on the scale of major terrestrial mountain ranges. Elevated ridges and blocky mountain chains have been identified in several regions, reaching heights of up to roughly 1 to 2 kilometers above the surrounding terrain. These mountains are composed of water ice, which at Titan's surface temperatures is as hard and rigid as silicate rock on Earth. The origin of these mountains is not entirely understood. Some may be remnants of ancient tectonic activity, formed when compressive or extensional forces cracked and uplifted blocks of Titan's icy crust. Others may be related to cryovolcanic processes, or to the erosion of an ancient, more heavily cratered surface. The relative scarcity of impact craters on Titan is itself a significant observation. Most solid bodies in the solar system display heavily cratered surfaces, records of billions of years of bombardment by asteroids and comets. Titan, by contrast, has very few confirmed impact craters. Cassini's radar identified only a small number of features that could confidently be classified as impact structures. And even those were often partially degraded, their rims softened, and their interiors filled with sediment or modified by erosion. The near absence of craters indicates that Titan's surface is geologically young, meaning that active processes are continuously resurfacing the Moon, erasing the record of past impacts. Several mechanisms could be responsible for this resurfacing. Aeolian processes, the movement and deposition of wind-blown organic sediment, can bury craters over time. Fluvial erosion, the carving and filling action of methane rivers, can modify crater rims and fill crater floors with transported material. Cryovolcanism, if it occurs, could resurface areas with flows of water-ammonia mixtures or other volatile materials erupted from the interior, and tectonic processes could deform and displace the surface. The combination of these mechanisms appears to keep Titan's surface in a state of continuous renewal, making it one of the geologically youngest surfaces among the solid bodies of the outer solar system. Some of the most intriguing and debated surface features on Titan are those that have been tentatively identified as cryovolcanic in origin. Cryovolcanism, as the name implies, is volcanism involving volatile substances rather than molten rock. On a world made largely of water ice, with a subsurface reservoir of liquid water and possibly ammonia, cryovolcanism would involve the eruption of water, ammonia, water mixtures, or other volatile fluids onto the surface, where they would freeze rapidly in the extreme cold. If such eruptions occur on Titan, they would produce features analogous to lava flows and volcanic edifices on Earth, but composed entirely of frozen volatiles. Cassini identified several surface features that were proposed as possible cryovolcanic structures. The most widely discussed is a region called Sotra Patera, which shows a combination of features suggestive of volcanic activity. These include a deep depression resembling a volcanic caldera, adjacent elevated terrain resembling a volcanic shield, and lobate flow-like features radiating outward from the summit region. Infrared observations indicated that the composition of the flow-like features differed from the surrounding terrain, consistent with material that had been emplaced from below rather than deposited from the atmosphere. However, the interpretation of Sotra Patera and similar features remains debated. The resolution of Cassini's instruments, while remarkable given the distance and the challenges of observing through Titan's atmosphere, was not sufficient to conclusively confirm a volcanic origin. Alternative explanations, including tectonic disruption, erosional modification, or mass wasting, could account for some of the observed morphology. The question of whether Titan is cryovolcanically active remains open, and resolving it is one of the priorities for future exploration. If cryovolcanism does occur on Titan, its implications would be profound. It would provide a mechanism for replenishing atmospheric methane, as methane trapped in the subsurface could be released during eruptions. It would indicate that Titan's interior remains geologically active, driven by tidal heating from Saturn or residual heat from formation, and it would create transient environments where liquid water from the subsurface might briefly exist on or near the surface before freezing, offering potential habitats where water and the abundant organic molecules on Titan's surface could interact. Beyond the major features of dunes, mountains, craters, and possible cryovolcanoes, Titan's surface includes large regions of varied terrain that Cassini could characterize only broadly. Bright terrain at mid-latitudes may represent areas of exposed water ice, cleaned of organic deposits by erosion or weathering. Dark terrain may represent thick accumulations of organic sediment. Some regions show labyrinthine terrain, complex patterns of ridges and valleys whose origin is uncertain. Others show relatively flat, featureless plains that could be ancient lake beds, eroded plateaus, or surfaces buried under uniform deposits of atmospheric fallout. The variety of Titan's surface geology reflects the diversity of processes acting on it. Wind, liquid flow, atmospheric chemistry, possible volcanism, possible tectonics, and impact cratering all contribute to shaping the landscape. No single process dominates. Instead, Titan's surface is a record of competition and cooperation between multiple geological agents, each leaving its signature in the terrain. The result is a world that, despite being a frozen moon orbiting the sixth planet from the sun, displays a geological complexity that rivals many rocky worlds far closer to the sun. This complexity is what makes Titan's surface so difficult to interpret from orbit and so enticing for future exploration. Every feature raises questions that Cassini's instruments could approach but not fully answer. What exactly are the dune grains made of? How deep are the organic deposits? What lies beneath the surface at the equator? Is the bright terrain truly exposed water ice? Are the labyrinthine terrains carved by fluid, collapsed by subsurface processes, or built by some mechanism not yet understood? Is there cryovolcanic activity happening today, or is the surface shaped only by wind, rain, and slow sedimentation? The answers to these questions await a closer look, a look that only a surface mission could provide. Beneath the frozen surface of Titan, beneath the dune fields and the riverbeds, and the organic sediments that blanket the equator, beneath even the rigid crust of water ice that forms the structural foundation of the moon, there is strong scientific evidence for the existence of something remarkable. An ocean, not of methane, not of ethane, an ocean of liquid water. The idea that Titan might harbor a subsurface ocean predates the Cassini mission, but it was Cassini's measurements that elevated the hypothesis from theoretical speculation to near certainty. The evidence came from multiple independent observations, each pointing toward the same conclusion. The interior of Titan is not entirely solid, and a layer of liquid separates the outer ice shell from the deeper interior. The most compelling evidence came from Cassini's precise tracking of Titan's gravitational field and its rotational behavior. As Cassini made repeated close flybys of Titan, subtle shifts of spacecraft's velocity, measured through the Doppler effect on its radio signal, allowed scientists to map the distribution of mass within the moon. These gravity measurements revealed that Titan's interior is not uniform. The density increases toward the center, consistent with a differentiated body in which heavier materials, primarily rock and possibly an iron-rich core, have sunk toward the center, while lighter materials, primarily water ice, have risen to form the outer layers. But the gravity data alone did not prove the existence of a liquid ocean. The critical additional evidence came from measurements of Titan's tidal response. Titan orbits Saturn in a slightly elliptical orbit, meaning its distance from Saturn varies over the course of each orbital period of approximately 16 days. As Titan moves closer to and farther from Saturn, the planet's gravitational pull creates tidal forces that distort the moon's shape, stretching it slightly along the axis pointing towards Saturn, and compressing it along the perpendicular axes. The magnitude of this tidal distortion depends on the internal structure of the body. A completely solid body would deform only slightly because the rigidity of solid ice resists the tidal forces. A body with a liquid interior would deform much more because the liquid layer allows the outer shell to flex and respond to the changing gravitational pull. Cassini's measurements of Titan's tidal deformation indicate that the surface rises and falls by approximately 10 meters over the course of each orbit. This is far more than would be expected for a completely solid body of Titan's size and composition. The measured tidal response is consistent with a model in which a global ocean of liquid water exists beneath an outer shell of ice, allowing the shell to flex in response to Saturn's tidal forces. The ocean does not need to be thick for this effect to occur. Models suggest a water layer, perhaps 50 to 100 kilometers deep, lying beneath an ice shell of similar thickness, though the exact dimensions remain uncertain. Additional support came from Cassini's observations of Titan's rotation. Careful measurements of the positions of surface features across multiple flybys revealed that the surface of Titan does not rotate at precisely the same rate as the Moon's orbital period. Instead, the surface appears to shift slightly relative to the expected position, as though the outer shell is not rigidly connected to the deeper interior. This phenomenon, called non-synchronous rotation, is most naturally explained by the presence of a liquid layer between the surface and the interior, allowing the outer ice shell to slip and rotate independently of the rocky core beneath. The effect is subtle, amounting to a fraction of a degree over years of observation, but it is measurable and consistent with a subsurface ocean. The existence of this ocean raises extraordinary questions about chemistry and habitability. Titan's surface is covered with organic molecules, the products of billions of years of atmospheric photochemistry. These organics accumulate on the surface, are transported by rivers, deposited in basins, mixed with ice, and buried by geological processes. If any mechanism exists to bring these organic molecules into contact with the liquid water beneath the surface, the resulting chemistry could be remarkable. Water is the solvent in which the chemistry of life as we know it operates. Organic molecules are the building blocks from which biological molecules are constructed. On most worlds, these two ingredients are separated. Rocky planets have water but limited organic chemistry. Icy moons may have water oceans but lack the rich organic surface chemistry that Titan possesses. Titan is unusual precisely because it has both. Its surface is arguably the most organically rich surface in the solar system outside of Earth, and beneath that surface lies an ocean of liquid water. The question is whether these two reservoirs interact. If they do, even occasionally, the implications for prebiotic chemistry are profound. Impact events could provide one mechanism. When a sufficiently large asteroid or comet strikes Titan's surface, the energy of the impact could melt through the ice shell, creating a transient melt pool that mixes surface organics with subsurface water. The resulting mixture would be a warm, organic, rich, aqueous solution, precisely the kind of environment in which prebiotic chemical reactions might occur. Such a melt pool would eventually refreeze, but depending on its size, it could remain liquid for thousands or even tens of thousands of years, potentially long enough for complex chemistry to develop. Cryovolcanism, if it occurs, could provide another mechanism. Eruptions of water or water ammonia, mixtures from the subsurface onto the organic rich surface, would create temporary environments where water and organics coexist as liquids. These environments would be transient, freezing relatively quickly in Titan's extreme cold, but even brief periods of mixing could produce chemical products of interest. Scientists have explored these possibilities through laboratory experiments on Earth. Researchers have mixed tholin-like organic materials with liquid water and ammonia under conditions designed to simulate what might happen during an impact event or cryovolcanic eruption on Titan. The results have been striking. When tholins are exposed to liquid water, they undergo hydrolysis, a chemical reaction in which water molecules break apart larger organic molecules into smaller, more biologically relevant fragments. Among the products detected in these experiments are amino acids, the molecular building blocks of proteins, as well as other compounds of prebiotic significance. These experiments do not prove that life exists on Titan. They do not even prove that prebiotic chemistry has occurred there, but they demonstrate that the raw materials present on Titan's surface are capable of producing biologically relevant molecules when exposed to liquid water. If nature has provided opportunities for such exposure, even rarely, Titan may harbor one of the most interesting prebiotic chemical environments in the solar system. The composition of the subsurface ocean itself is another area of active investigation. Pure liquid water would freeze at the temperatures expected within Titan's interior, without some mechanism to lower the freezing point. The most widely proposed antifreeze agent is ammonia. If the ocean contains a significant fraction of dissolved ammonia, its freezing point could be depressed by tens of degrees, allowing it to remain liquid at temperatures well below the normal freezing point of water. Ammonia is abundant in the outer solar system and was likely present in the materials from which Titan formed, making its presence in the subsurface ocean plausible. An ammonia water ocean would have different chemical properties than a pure water ocean. The pH would be more alkaline. The solubility of various organic compounds would differ. The types of chemical reactions that could occur would be influenced by the presence of ammonia as both a solvent component and a potential reactant. Whether these differences would enhance or inhibit prebiotic chemistry is not yet clear. Some researchers have argued that ammonia-water mixtures could actually facilitate certain prebiotic reactions by providing nitrogen-containing molecules in a reactive liquid environment. Others have suggested that the extreme cold and the chemical properties of concentrated ammonia solutions might limit the complexity of chemistry that could develop. Beyond the water ammonia ocean, Titan's interior likely contains a rocky core enriched in silicate minerals and possibly metallic iron. The boundary between this rocky core and the overlying ocean is another environment of potential interest. On Earth, interactions between seawater and oceanic crust at hydrothermal vents produce chemical gradients and energy sources that support thriving ecosystems entirely independent of sunlight. If similar interactions occur at the base of Titan's ocean, where liquid water meets warm rock, they could provide energy and chemical nutrients that might support simple chemistry or, in the most speculative scenarios, rudimentary biological activity. It is important to approach these possibilities with scientific caution. There is no evidence that life exists on Titan. The surface temperatures are far too cold for any known biological process. The subsurface ocean, if it exists as current evidence strongly suggests, may be habitable in the most minimal sense of the word, meaning it could potentially support liquid water chemistry, but whether it actually hosts any form of life is entirely unknown. The gap between having the right ingredients and actually producing life is enormous, and it is a gap that science has not yet fully bridged even for Earth, where life clearly did arise. What makes Titan scientifically valuable in this context is not the certainty of biological activity, but the opportunity to study prebiotic chemistry in a natural setting. Earth's own prebiotic chemistry has been largely erased by 4 billion years of biological activity. The chemical conditions that existed on early Earth before life began have been overwritten by life itself. Titan, by contrast, may preserve a record of prebiotic processes operating over geological time, uncontaminated by biology. If scientists can study the organic chemistry of Titan's surface and understand how it interacts with water when the two are brought together, it may illuminate the steps that led to life on Earth, or reveal alternative chemical pathways that could lead to life under very different conditions. This is why Titan occupies such a prominent position in the field of astrobiology. Not because scientists expect to find organisms swimming in its methane seas or lurking in its subsurface ocean, though neither possibility can be entirely excluded, but because Titan offers a natural laboratory for studying the chemistry that precedes biology. It is a world where the building blocks of life are manufactured in the atmosphere, deposited on the surface, and potentially mixed with liquid water beneath the crust, all within a setting that can be studied by spacecraft and eventually by landers and analytical instruments, far more capable than anything yet sent there. The subsurface ocean also connects Titan to a broader family of ocean worlds in the outer solar system. Europa, Ganymede, Enceladus, and possibly several other icy moons are believed to harbor subsurface oceans of liquid water. Each of these worlds offers a different window into the question of habitability beyond Earth. Europa's ocean is in direct contact with a rocky seafloor and may have hydrothermal activity. Enceladus actively vents ocean material into space through geysers at its south pole. Ganymede ocean may be sandwiched between layers of ice, limiting its contact with rock. Titan's ocean is distinguished by the extraordinary richness of the organic material that overlies it, creating a unique combination of water and organics found nowhere else. Together, these ocean worlds represent one of the most exciting frontiers in planetary science. They suggest that liquid water is not rare in the solar system. It is common. Hidden beneath ice shells, sustained by tidal heating and internal processes, liquid water may be present on half a dozen or more worlds in our solar system alone. The implications for the possibility of life beyond Earth are significant, and Titan, with its combination of organic chemistry and liquid water, stands among the most promised candidates for further investigation. The ocean beneath the patient, it has existed for billions of years, insulated from the cold of space by a thick shell of ice, warmed from below by the slow decay of radioactive elements in the rocky core, and by tidal energy from Saturn's gravitational embrace. It does not announce itself. It does not erupt spectacularly as Enceladus does. It simply persists quietly in the dark interior of a moon that already has more than enough complexity on its surface to justify a lifetime of exploration. What happens where that water meets the organic rich ice above it, and what happens where it meets the rocky core below, are questions that may define the next great chapter of solar system exploration. And it is to that future chapter that we now turn. The exploration of Titan did not end when Cassini's mission concluded. On the 15th of September 2017, after 13 years orbiting Saturn, Cassini was deliberately plunged into Saturn's atmosphere, where it burned up and disintegrated. The decision to destroy the spacecraft was itself an act of scientific responsibility. Cassini's fuel was nearly exhausted, and without the ability to control its trajectory, there was a risk that the spacecraft might eventually collide with Titan or Enceladus, both of which are considered potentially habitable environments. Rather than risk contaminating those worlds with terrestrial microbes that might have survived on the spacecraft, mission controllers chose to dispose of Cassini in Saturn's atmosphere, where no contamination risk existed. The loss of Cassini left a silence in the Saturn system. No spacecraft currently orbits Saturn. No instruments are watching Titan's weather change, mapping new sections of its surface, or monitoring the slow seasonal evolution of its methane seas. The data Cassini collected continues to be analyzed, and new discoveries are still being made from that data years after the mission ended. But the active exploration of Titan paused, and for a time, the question of when humanity would return remained unanswered. That answer came in June of 2019, when NASA announced the selection of a mission called Dragonfly. Unlike any spacecraft previously sent to another world, Dragonfly is a rotorcraft lander. It is, in essence, a drone, a nuclear-powered, instrumented autonomous flying laboratory designed to land on Titan's surface and then fly from location to location, covering distances of kilometers, with each flight exploring the moon's diverse terrain in a way that no stationary lander or slow-moving rover could achieve. The concept behind Dragonfly exploits one of Titan's most distinctive characteristics. The combination of a thick atmosphere and low gravity makes powered flight on Titan remarkably efficient. Titan's atmosphere is approximately 4 times denser than Earth's at sea level, and its surface gravity is roughly 1/7 of Earth's. Together, these factors mean that a rotorcraft on Titan requires far less power to stay aloft than an equivalent vehicle would require on Earth. The same physics that makes methane raindrops fall slowly and allows massive dune ridges to be shaped by gentle winds also makes it practical to fly a scientific laboratory from one site to another across the surface of a moon nearly 1.5 billion kilometers from home. Dragonfly is designed as an octocopter with 8 rotors arranged in 4 coaxial pairs. The vehicle is half the size of a large terrestrial drone or a small car, and it carries a suite of scientific instruments designed to address the most important questions that Cassini left unanswered. These instruments include a mass spectrometer capable of identifying the molecular composition of surface materials, a gamma ray and neutron spectrometer for determining elemental composition of the ground beneath the lander, a suite of meteorological sensors for measuring atmospheric conditions at the surface, cameras for imaging the surrounding terrain at close range, and a seismometer for detecting any seismic activity that might reveal information about Titan's interior structure and the subsurface ocean. The mission's scientific objectives are centered on understanding Titan's chemistry and assessing its prebiotic potential. Dragonfly will sample surface materials at multiple locations, analyzing the composition of the organic sediments that blanket the equatorial regions, the water, ice, bedrock where it is exposed, and any materials that might represent mixtures of organics and water, such as material excavated by impact craters. By moving between geologically distinct sites, Dragonfly will build a comprehensive picture of how Titan's surface chemistry varies from place to place and how different geological processes have modified the organic material deposited from the atmosphere. The selected landing site is a region called Shangri-La, one of the large equatorial dune fields identified by Cassini's radar. Shangri-La offers relatively flat terrain, suitable for initial landing and early flights, as well as access to organic-rich dune material for sampling. From Shangri-La, Dragonfly is planned to make a series of flights covering progressively greater distances, eventually reaching a large impact crater called Selk. Selk crater is a particularly compelling target because impact craters on Titan represent natural experiments in prebiotic chemistry. When the impactor struck Titan's surface, the energy of the collision would have melted water ice from the crust, creating a transient pool of liquid water mixed with the organic material that covers the surface. This warm, organic-rich melt pool would have persisted for an extended period, potentially thousands of years, depending on the crater's size, before eventually refreezing. During that time, the mixture of water and organics could have undergone the same kinds of hydrolysis reactions that laboratory experiments have shown to produce amino acids and other biologically relevant molecules from tholin-like materials. By the time Dragonfly arrives, the melt pool will have long since frozen, but the chemical products of those reactions may still be preserved in the crater floor materials. Analyzing these materials could reveal whether Titan's natural processes have indeed produced prebiotic molecules, providing direct evidence of prebiotic chemistry occurring on another world. This is one of the most scientifically significant measurements that Dragonfly could make, and it is one of the primary reasons Selk crater was chosen was chosen as the mission's ultimate destination. The journey from Shangri-La to Selk crater covers approximately 175 kilometers. Dragonfly will not make this trip in a single flight. Instead, it will hop from site to site, spending time at each location to conduct measurements and recharge its batteries using its radioisotope thermoelectric generator, the same type of nuclear power source that sustained Cassini and the Voyager spacecraft. Each flight is expected to cover roughly 8 kilometers, with the vehicle flying at altitudes of a few hundred meters to a few kilometers above the surface between flights. The lander will rest on the surface, conducting science measurements and recharging for the next hop. The total planned mission duration at Titan is approximately 2.5 Earth years, during which Dragonfly is expected to cover a total distance greater than all the Mars rovers combined. The comparisons is striking. In nearly 2 decades of operation on Mars, the various rovers have collectively traveled a few tens of kilometers across the Martian surface. Dragonfly, in under 3 years, is designed to cover well over 100 kilometers on a world 10 times farther from the Sun. The power source deserves particular attention. Solar panels are not viable at Saturn's distance from the Sun. The sunlight that reaches Titan is approximately 100 times weaker than at Earth, and even that feeble illumination is further reduced by the thick atmospheric haze. Any long-duration surface mission on Titan must rely on nuclear power. Dragonfly carries a multi-mission radioisotope thermoelectric generator, which converts the heat produced by the natural decay of plutonium-238 into electrical power. This power source provides a steady, reliable supply of electricity, regardless of weather, time of day, or atmospheric conditions. It is the same fundamental technology that has enabled every major outer solar system mission, from Viking to Voyager to Cassini to New Horizons. Dragonfly is currently scheduled to launch in 2028, with arrival at Titan expected in the mid-2030s after a journey of approximately 6 years. The long transit time is a consequence of the immense distance to Saturn and the trajectory required to reach it. When Dragonfly arrives, it will enter Titan's atmosphere directly, using a heat shield and parachute system, similar in principle to Huygens, before deploying its rotors and making a powered descent to the surface. The timing of Dragonfly's arrival has been carefully chosen to coincide with a period of relatively calm weather at the landing site. Titan's equatorial region is expected to be in a dry period during northern winter, with minimal cloud activity and low probability of methane precipitation. This provides favorable conditions for flight operations and surface measurements. As the mission progresses and Titan's seasons advance, weather conditions may change, providing opportunities to observe seasonal atmospheric phenomena directly from the surface. Beyond Dragonfly, scientists have proposed other future missions to Titan that would address questions even Dragonfly cannot answer. Concepts have been studied for boats or submarines that could navigate Titan's methane seas, directly sampling the liquid and measuring its depth, composition, temperature, and currents. A submarine mission to Kraken Mare, for example, could explore the largest body of liquid on Titan, mapping its seafloor, studying its chemistry, and searching for any signs of unusual activity. Such a mission remains conceptual, but the engineering challenges, while significant, are not insurmountable. The thick atmosphere would allow the vehicle to communicate with an orbiter or relay satellite, and the liquid methane environment, while extremely cold, is chemically benign compared to the sulfuric acid clouds of Venus or the intense radiation environment near Europa. Other proposed concepts include long-duration atmospheric balloons that could float in Titan's atmosphere for months, carried by winds across the globe, studying weather patterns, atmospheric chemistry, and surface features from above. A balloon in Titan's thick atmosphere could carry substantial scientific payloads and cover vast distances without requiring propulsion, simply drifting with the prevailing winds, while instruments observe the world below. Such a mission could provide global atmospheric data that neither an orbiter nor a surface lander could obtain. Orbiter concepts have also been proposed, missions that would return to Saturn and establish long-term monitoring of Titan from orbit, carrying instruments more advanced than Cassini's. A dedicated Titan orbiter equipped with higher resolution radar, advanced spectrometers, and possibly even ice-penetrating radar capable of detecting the subsurface ocean directly, could answer questions about Titan's interior structure, ocean depth and composition, surface geology, and atmospheric dynamics with a level of detail far beyond what Cassini achieved. Each of these mission concepts addresses different aspects of Titan's complexity. Dragonfly will provide the first close-up surface measurements and the first direct chemical analysis of Titan's organic-rich terrain. A submarine would explore the methane seas. A balloon would study the atmosphere from within. An orbiter would provide global context. Together, they represent a potential program of Titan exploration that could span decades and fundamentally transform our understanding of this extraordinary world. For now, Dragonfly carries the immediate hopes of the Titan science community. It represents a bold step, not only in planetary exploration, but in the technology of exploration itself. Flying a drone on another world is not a minor engineering achievement. It requires autonomous navigation in an environment where communication delays make real-time control impossible. It requires flight systems that can operate reliably in temperatures far below those experienced by any aircraft on Earth. It requires instruments that can function in an atmosphere of nitrogen and methane on a surface covered with exotic organic chemistry, powered by a nuclear heart that must sustain the mission for years. But the rewards of reaching Titan's surface, of touching its organic sediments, of measuring the chemistry that has been accumulating there for billions of years, are immense. Dragonfly is not merely visiting another world, it is visiting a world that may hold clues to one of the deepest questions in science. How did the chemistry of life begin? What steps lead from simple molecules to the complex molecular machinery of biology? Is the path from chemistry to life inevitable given the right conditions, or is it a rare accident that occurred once and never again? Titan will not answer all of these questions, but it may illuminate parts of the path that have been invisible to us, preserved on a frozen moon, where the chemistry of life's origins has been running, slowly and patiently, for longer than life has existed on Earth. There is a particular quality to Titan that separates it from nearly every other world we have explored. It is not simply that Titan has an atmosphere, though that alone would make it exceptional among moons. It is not simply that it has rivers and seas, though those features place it in a category shared only with Earth. It is not simply the organic chemistry, or the subsurface, ocean, or the dune fields, or the seasons, or the weather. It is the way all of these things exist together on a single world, interacting with one another in ways that echo the processes we know from our own planet, while remaining fundamentally, beautifully alien. Titan is a world of translations. The water cycle becomes a methane cycle. The silicate rock becomes water ice. The sandy deserts become fields of organic particles manufactured by the sky. The geology driven by volcanic heat on Earth becomes, on Titan, a geology potentially driven by eruptions of water and ammonia from a hidden ocean. Every familiar process has been reimagined in a different chemical language, operating at temperatures so low that the familiar substances of our world, water and rock and air, take on entirely different roles. Water is stone, methane is rain, Organic molecules fall like snow from an atmosphere that manufactures them continuously, year after year, for billions of years. This translation is what makes Titan so scientifically valuable. By studying a world where the same physical laws produce the same categories of phenomena using entirely different materials, scientists can distinguish between the principles that are universal and the details that are specific to Earth. River networks form on Titan because flowing liquid erodes solid surfaces, not because water specifically is required. Dunes form because wind transports granular material, not because silicate sand is required. Weather cycles operate because a volatile substance can change phase between liquid, solid, and gas at the conditions present on the surface, not because water specifically must be that substance. Titan demonstrates that these processes are consequences of physics, not of chemistry. They will occur wherever the conditions allow, regardless of which molecules play which roles. This insight extends to the question of prebiotic chemistry. On Earth, the path from simple molecules to the first living cells remains one of the greatest unsolved problems in science. We know that it happened because we are here, but the specific sequence of chemical steps, the environments in which they occurred, the time scales involved, and the degree to which the outcome was inevitable or accidental remain deeply uncertain. Earth's own geological record from that era has been almost entirely destroyed by billions of years of plate tectonics, volcanism, erosion, and biological activity. The evidence has been overwritten. Titan offers something that Earth cannot: a world where prebiotic chemistry may still be in progress, uncontaminated by biology, operating on a surface that has been accumulating organic material for the entire history of the solar system. If the chemical steps that precede life are a natural consequence of organic molecules interacting with liquid water, then Titan, where those ingredients exist and occasionally meet, might preserve a record of those steps in a way that Earth no longer can. Studying Titan's chemistry is, in a sense, studying Earth's distant past, preserved on a frozen moon where the clock of prebiotic evolution has been running slowly and has never been reset. Whether that chemistry has progressed beyond the simplest stages remains entirely unknown. Perhaps the organic molecules on Titan's surface have never encountered liquid water in sufficient quantities or for sufficient durations to produce anything of biological relevance. Perhaps the cold temperatures have slowed every reaction to the point of insignificance. Perhaps Titan's prebiotic potential is purely theoretical, a possibility that physics allows but nature has never realized. These are honest uncertainties, and no current evidence resolves them. But the possibility alone is enough to justify the continued exploration of this world. Science advances not only by confirming what we expect, but by investigating what we do not yet understand. Titan is a world that we do not yet understand. Despite everything Cassini and Huygens revealed, we have mapped its seas from orbit, but never sailed them. We have identified organic molecules in its atmosphere, but never analyzed the sediments that accumulate on its surface. We have inferred a subsurface ocean from gravitational measurements, but never detected it directly. We have proposed that prebiotic chemistry might occur in impact melt pools, but never sampled the material within a crater to test the hypothesis. Every major question about Titan remains open, and each of those questions connects to larger questions about the solar system, about planetary science, and about the conditions that give rise to complexity in the universe. Titan is not merely an interesting moon. It is a laboratory for understanding how worlds work, how chemistry evolves, and how the ingredients of life distribute themselves across a solar system that is far richer, far more varied, and far more surprising than anyone imagined when the first telescopes were turned toward the sky. But tonight, as Saturn continues its slow orbit around the Sun, Titan follows faithfully beside it. The orange moon completes one revolution around its planet every 16 days, turning the same face toward Saturn at all times, its thick atmosphere glowing faintly in the distant sunlight. Beneath that atmosphere, the methane seas lie still in the polar darkness. The dune fields stretch across the equator, their ridges casting no shadows in the diffused, hazy light. Rivers wait in dry channels for rains that come infrequently but powerfully. And deep beneath the frozen surface, an ocean of liquid water persists in the darkness, warmed by the slow decay of radioactive elements and the patient gravitational pull of Saturn. Nothing hurries on Titan. The seasons take 7 years. The methane cycle turns on timescales that dwarf human lifetimes. The organic sediments accumulate particle by particle, building the surface over millions and billions of years. Even the potential chemistry of life, if it occurs at all in the brief windows, when water and organics meet, proceeds at a pace set by temperatures nearly 200 degrees below freezing. It is a world measured not in urgency but in patience, not in drama but in quiet persistence. A world where the most profound processes happen slowly, invisibly, beneath haze and ice and time. Christian Huygens could not have imagined any of this when he noticed a small point of light beside Saturn in 1655. He saw a moon. We now see a world with weather and geology and chemistry and oceans, a world that challenges our definitions of habitability and forces us to reconsider what we mean when we say, a place is alive with activity. Titan may never harbor life. It may already harbor the beginnings of something we do not yet have the tools to detect. Either answer would reshape our understanding of what is possible in the universe. For now, Titan waits. It has been waiting for 4.5 billion years. It is patient in a way that only worlds can be. And when we return, when Dragonfly descends through that thick orange sky and touches down on the dark organic surface for the first time, we will begin the next chapter of a story that started with a point of light beside a distant planet and led us to one of the most remarkable places the solar system has to offer. The rivers of Titan will flow again, the rains will fall, the seas will remain, and the questions that this quite extraordinary world has raised will, one by one, begin to find their answers.